I was laughing at this one. Cat 2 found to interfere with Apple Watch sensors. Ooh, I like this one. Okay, so the recorder has started, so I'm just gonna get started here. I'm pretty sure 90% of this class, or whoever is attending the lecture at this point, know what Slashdot is? Yes? No? No? Okay. So Slashdot is the original website for geeks. Okay, this is the first and original, and they post topics like this kind all the time. Sometimes it's political. Most of the time, it is at least somewhat related to technical stuff. And I was thinking, this one is kind of interesting. Australia to grade written essays in national exam with cognitive computing. In other words, instead of having people to grade written essays, they're going to use a computer to grade written essays. And this is not just to grade grammatical correctness. This is actually based on the content of the material. So right here, this is a link to the original article. And I think this is all kind of important stuff, because it kind of gives you an idea of where technology is heading and, actual application of stuff that we talk about in classes. So national schools test to be scored electronically from 2017. So 2 years from now, Australia will be grading written essays in English. Okay. So how would you like your English writing classes to be graded by a machine, by a computer, and is not touched by a human being? You don't like it, but you haven't even tried it yet.
Because for a few years, they just dump most of the stuff.
But you might get
submit, it doesn't actually check it correctly.
Yeah.
Because they're passing that testing phase. So most of the stuff, when you're one of those few people who are in the first year or two, you usually just lose the chances back to back. That's what happens.
Well, this type of research has been done for a long, long time. Okay, I remember when I first got to graduate school, which was 1989. My advisor was already doing research, or his advisor was already doing research in cognitive computing, which is basically the modeling of the human mind works. And in this case, in particular, to how do we read articles and how do we form arguments in our mind about what is the point of this article? What is it arguing for? What is it arguing against? And stuff like that. And the advisor of my own advisor, my grand advisor, was working on an AI engine, not only to read and understand editorial pieces from a newspaper, but also automatically form a opposing opinion and argue about the opposing opinion using AI, using artificial intelligence. And that was all done in Lisp. And that's why I learned how to use Lisp, because some of my original projects were of that nature. And that was 89, and now it is 2015. So how many years have passed? 26 years? So 26 years has passed, and we are now starting to see actual application of research, that was considered pretty much dead end at a time. Okay. Now I know it is considered a dead end because my own advisor, my first advisor did not get tenure, and then my alternate advisor, which I switched to later on, also did not get tenure. In fact, the entire AI group was disassembled. There was no one in charge of the AI group after these two professors did not get tenure. Okay, so it was considered a dead end kind of thing by 1989 or so. And yet now we start to see applications of some of those things. So it's interesting. Okay, interesting to me because I have a personal history that connects to this particular topic. But this is also interesting in many other ways because it means that Google can now read news articles for you. Okay, and you can just express. You can basically click yes, no, like, unlike. With each time Google makes a recommendation, And it can learn over time to figure out what you're interested in, what is your political position, what you believe in, what you do not believe in, okay? What type of things are the hot buttons for you, okay, to make sure that you will read it if I give you an article like that, okay? Which is good in a way because now you can be sent articles when you're interested in, but it's bad in a way because they can target you as well because they know your preferences, and so people can use Google, go through Google to target you and say, okay, I know this person is interested in these things, and we're not only talking about advertisement, we're also talking about political campaigns and other things that are not really just for money purposes. Are there any feedback from you guys about stuff like this? No? Yep.
I mean, I don't know anything about these technologies, so I guess it could work, but it seems not knowing anything like a bad idea because, first of all, how very can a computer be? I mean, you have probably thousands or tens of thousands of chips that are created, all of them are going to be different, and this is writing is something creative. It seems like it's going to produce like a very formulated, writing's already formulated enough as it is. And it seems like it's just going to take that to the extreme where the future generations taking these tests are going to figure out how this thing grades it or whatever, just write a certain way and everybody's going to be doing the same thing.
That's a good point. That's a good point, but that's assuming the engine is somewhat rigid and predictable.
Yeah.
Yep.
I think it's just uncomfortable to think that a computer can do creative work that previously only humans were thought to be able to do. And it kind of feels like at that point, it just pushes out and we're not needed anymore.
Well, but you have no idea what is computerized and what is not. Okay, Episode 7 of Star Wars could have been written completely by a computer, and they just stamped the name of George Lucas on it, right? You don't know. You have no idea, right? I mean, 50 years from now, they can release episode 27 for all we know, and you will still see Harrison Ford and other actors in that movie. But guess what? Those are not the actual actors. They just took images of the actors and have a 3D model that will continue to act way after the actor or the actress has passed away. Okay. It's not scary. What I find scary are the autonomous drones that can drop bombs. That scares me a little bit more than this kind of stuff. Okay, but we are definitely moving at an accelerated rate to more and more automation. Okay, there's no denying that. When I was in classes like you are at this point, there was no pipe dream whatsoever that AI would become reality. Okay, even voice recognition was more or less a pipe dream. Talk to a computer and have the computer to understand what words you're saying, not even the meaning. Okay, just pick out the right words from what you're saying. That was a pipe dream, back when I was in school. And that was just the 80s. Okay, I know to you that was a long time ago because my dad went to college about the same time. But in the grand scheme of things, it's not that long ago. Okay, if you think about 200 or 300 years ago, okay, just think back 300 years ago, and at a certain time, and you think back 50 years or 100 years earlier, how much has changed? In other words, comparing, let's say, 1750 to 1700. Of those 50 years, how much do you think has changed? Not a whole lot. Okay, right? Fashion might have changed. Okay? Nobles and rich people, the way they dress might have changed a lot, but the way you farm is going to be the same. Okay, it's still going to be the same, farming equipment, the same way of doing things. Not much has changed. So today, 50 years is a long time. Okay, what is the current version of Android? I know the answer to that one, so I can ask. 5.1. Yeah, Lollipop, but it's 5.1. It's Cyanogen Module 12.1, which is mapping to Android 5.1. When did the first Android device came out, which was kind of clunky and not so useful at the time? Was it 10 years ago? Was it even a decade? No, it's less than a decade. Okay, so we are definitely looking at a accelerated rate of progress here. And people will find applications as computation power becomes more of a reality. These things are not practical only because we did not have the computation power back then. Okay, if you compare this, what you have on your cell phone, in terms of horsepower, computation power, compared to a workstation or even a mainframe computer back 26 years ago, you have more processing power on your cell phone than most workstations, even the high-power workstations 26 years ago. So a lot of things that were considered impractical, not doable, or anything like that is now practical. It's actually doable. Okay, and this curve seems to be continuing. Okay, Moore's law does not seem to be slowing down at all. Okay, so you can expect the exponential growth to continue, which also means more and more things that we consider as impractical cannot be done even by today's standard. Okay, 20 years from today, it will become like reality. People will just take it for granted. Self-driving cars, mark my words. Okay, you can tell these to your kids. You can say, well, 20 years ago, my professor said, self-driving cars will be taken for granted 20 years ago. And then 20 years later, which is 2035, okay? Just if for those of you who still remember, okay, in that year, okay, at about this today, think back and say, well, I guess somebody did say something about we'll take self-driving cars for granted, because I think self-driving cars will be the norm in 20 years, if that. Okay, it would take that long. It would take less time, I think.
They're pretty good now as well.
Huh?
Google Car is pretty good at driving by itself already.
Google Car is a good prototype. It's a good proof of concept. But all Teslas can self-drive already. Every single Tesla that's rolling out of the production line today can self-drive. It's just the regulation, the law, the legal stuff that is preventing those cars from self-driving. And I know those are expensive cars, but you can probably tell how fast technology can become inexpensive. How much was a laser printer when they first came out? Super expensive, right? It only big companies can afford it. How much are those laser printers today? You go to Fry's, okay, today, and you walk up to an associate and say, give me the best deal on laser printers. How much are you paying for a laser printer? $80, if that, right? 75, 60 bucks. The toner costs more, right? the toner cartridge, which you will have to replace after like half a rim of paper, because they give you the econo version to the trial version, so it's only good for like a few hundred pages, and then after that you have to pay like 70 bucks to buy a toner cartridge for a $60 printer, right? That's the usual scheme. But it's still significant how much you have to pay today for a laser printer. It's basically the same technology as 20, 30 years ago. But 30 years ago, a laser printer looks like what? A fridge. And not the small one at that either, okay? And it's a lot heavier than a refrigerator. So these things are all coming. I know it's not directly related to graph theory or discrete math and anything like that, but all of this stuff is actually coming. Yep, go ahead.
Do you know what sort of AI they are using?
What sort of AI? I do not know. I have not read into the article to find out whose research it is based on. But I would not be surprised if it has connection back to my grand advisor. Maybe another branch of his students. Basically continue the research and actually produce something that is
Their
practical.
AI should be learning, right? Their AI should learn in the first place how to figure out different types of writing.
It does
not
not
many of
really.
them actually learn.
Well, the one that I was familiar with did not quote unquote learn. Its job is to analyze. So it breaks apart the sentences and it tries to understand the concept underneath. And then it will also read another article or be able to actually compose, in this case, a counter article to an editorial. It's definitely very limited at the time when, back 26 years ago, it was really limited. But I think today, if they can propose this, by year 2017, I think they're pretty close to it. And if you think about it, turning in is already doing a little bit of AI because they have to find plagiarism. But that's an easier problem to solve because they can pick out unusual combination of words or sentences and say, okay, can we find anything like that somewhere else, right? I have no idea how turning in works. Do you guys know whether it's effective or not? Do you know of people who got caught? Okay, it is.
It actually finds the actual sentence over the internet and actually references on the highlighted text on the bottom that where it is, how many words did you copy, how many percent of the text is actually copied from.
Okay.
So I would get a small percent because I guess there's a high school student in Missouri with the same name as me. So it's like, oh, 1% plagiarism, same name, it picks out that part.
Okay. But if you rephrase a sentence, would it still be able to pick up and say it's basically the same thing, except it is?
We may pick it up, but the thing is like the percent of the plagiarism will go down.
Okay. Like if the original sentence is using active tense and you turn it into passive tense, which is pretty easy.
Probably follow on.
So it will still be able to recognize, hey, this is a modified version of that, right? That's actually pretty good. Yep.
As long as you rephrase, like you change some of the words, but wouldn't really organize what you're writing.
Well, you know what? That really brings us to one of the topics that I was planning to talk about today, which is called a minimum spanning tree. So we'll get to that after we get through the fixed stuff about graph theory. The only part that we haven't really talked about in graph theory are the terms of a graph theory. I think we went over this maybe a little bit. The order of a graph, G, is the cardinality of the vertices. Did we talk about this? Maybe not, huh? We'll just kind of quickly go over this. These are just definition of terms, so there's no proof, nothing really to explain here. A graph G is called simple if and only if for all pairs of V and W in the vertex, the set of vertices, the cardinality of this particular set is less than or equal to 1. Okay, so let's see if we can interpret this part here, the highlighted portion here. So this particular set is basically saying each element E has to be an element of the edge set, and on top of that, E is VW or WV, which means in the quadratic graph, it simply means that these two vertices are connected. You can go from one to the other, okay? And this number has to be less than or equal to 1 when a graph is called simple. So what does that mean? Well, I mean, I have that sentence right next to it. In other words, there's only up to one edge between any two vertices. That's basically what it is. Okay. Because in certain graphs, which is called a multigraph, well, that's the next point here. A graph that is not simple is called a multigraph. Most graphs that we deal with are simple. Okay, multigraphs are actually fairly rare, that we need a multigraph to represent a particular problem. The size of a graph, okay, this is how we measure the size of a graph. It is not the same as the order of a graph. It is actually measured by the number of edges in the graph, not by the number of vertices in the graph. That's because the total number of edges can be up to be the total number of vertices squared, even for a simple graph. That would make everything connected. But it can also be very small if you have a tree, which we'll talk about today. The complement of a graph is represented by the G with a bar on top of it, where you have the same vertices, except you have the complement of edges. So if there is an edge between two vertices in G, that will be missing in the complement. If there's no edge between two vertices in G, then G bar would have that edge. So it's basically exactly the opposite, but from the perspective of edges, not from the perspective of vertices. Is that concept okay? I mean, I'm just kind of casually explaining the concepts. Okay. Two vertices V and W are adjacent in the graph if and only if there exists an edge VW in the edge set, or there exists another edge WV in E. So they're basically quote-unquote adjacent when one connects to the other. That's how we define the term adjacency. And it's also called, one is called a neighbor of the other one. That's how we define neighborhood as well in the graph. In the graph, this particular edge, in an edge VW, V is known as the tail and W is known as the head. I know this sounds like a typo or a misunderstanding of the concept, but that actually is true, and that has to do with the design of an arrow. Because the arrow head is going to the destination, and that's why the destination of an edge is called the head of the edge, and then the tail of the edge is the originating vertex of an edge. Is that okay so far? Because this one is counterintuitive. It is not the usual way of thinking about head and tail. So think of the arrow connecting two vertices, and that's how we define the head and the tail. In a graph, VE, the in degree of a vertex is basically the number of edges that are incoming into that particular vertex. So the way that I express it is it is the cardinality of a set. Okay, but when you look at this set here, you will ask, okay, but what qualifies to be an element in this particular set? Each element has to be first an element of the edge set, okay? But on top of that, we have a second criteria, which is basically it has to be an edge where it is going into the vertex V, not going out of the vertex E. Okay? That's called the in degree or connectivity, or basically the number of edges going into a particular vertex. So the next one is pretty easy. The next one is just the opposite. The out degree of a vertex is basically the number of edges going out of a particular vertex. These are just terminology stuff. It's really just definitions. The graph G is considered complete if and only if for all pairs of V and W in V in the set of vertices, if V does not equal to W, if we are not talking about the same vertex, then there's an edge between those two. In other words, there exists an edge between every two different vertices. That's all I'm saying. That will make the graph what we call complete. Self loops are excluded, which means you cannot have a vertex going from V to V. That's basically what a self loop is. Yep.
So looking at the notation for the in degree, it looks like the vertex or the edge has to be coming into the head.
Yes, that's the whole idea because it's an arrow.
So it has to be coming. So the in degree is edges coming into the head, and the out degree is edges going out from the tail.
Yep, because arrows are drawn this way, so that makes this node the head with respect to these three edges.
I was just making sure I understand.
Yep. All right. Okay. Now we talk about walks. A walk W of a graph G is an n-tuple. Okay, so the first thing we notice is it is not a set of vertices, it is a tuple of vertices. What is the main difference between a tuple and a set? Order matters, okay? And then the second thing is the same element can appear multiple times in a tuple, but it can only appear exactly once in a regular set. Okay, so those are the main the differences here. This one is definitely a tuple, which means you can have the same vertices appearing multiple times within the tuple itself. And what I do is I use the square bracket notation to indicate which element within a tuple we are talking about. And it is zero oriented in this case, so it's like in C and C++. So in this case, I would basically say right here. So for all I such that I, this is just a long way of saying I is a natural number, and it is less than bar W bar, which is the length of the tuple minus 1. In other words, for all valid indexes, okay, minus the last one, this particular edge has to exist in E. In other words, all of the edges are connected. So if you think about the graph, okay, if you just think about the graph, I'm just going to give you a simple one here. Okay, so we have 5 vertices, and this head is going out. Let me try this one. That's better. So if you look at the graph only that has 5 vertices, we'll just go ahead and draw some edges around here. we'll just store it like that. A walk is basically just it's a tuple or a sequence of vertices where the edges are connected. So if we label this one as 1, A, B, C, D, and E, and let's start with A as our the origin of the entire walk. I can create a walk like A, B. Now from B, I only have one choice to go to C, because you can see that B is only having one outgoing edge to C. And then from C, I can go back to E. Then I can go back to A, and go back to B, go back to C, and this time I go to D. This is perfectly okay as a walk, because the only requirement for a walk is, if you look at all of these vertices, between any two vertices within the tuple, the edge has to exist. Well, do we have an edge AB here? Do we have an edge BC? CE, CEA, AB, BC, and CD. So even though we have a cycle here, which means we went around a loop, it's okay. You can actually go through a loop as many times as you want. It will still be called a walk. Are we doing okay so far? So if you want to remember what a walk is, just think about a stroll in the park, okay, where you might want to go through the same place several times, in a cycle, okay. So a walk can have loops, can have cycles. Well, but sometimes you may not want to have repetitions. So in that case, it is called a path. So a path is essentially a walk, but it has one additional qualification. It cannot contain any repetitions. In other words, in this case, I use the set notation and all of that stuff to express the same thing. So in this case, if you look at the I is representing an index into the walk itself, into the path for every single element, and then J is going up to, but excluding P itself. So if I does not equal to J, then P bracket I cannot equal to P bracket J, which basically means you cannot have repeating elements within the n tuple. Is that okay? It's just a long way of saying you cannot have duplicate vertices within the tuple. A trail is a walk where no edges is repeated. So you can have a path where an edge is, an edge cannot do that. But a trail is a walk where no edges is repeated, but you can repeat the same vertex. So you can revisit the same vertex. As long as you're not repeating the same edge, it will still consider it a trail. Is that okay? Let's see if we can find a trail in this particular example where you can repeat an edge but not a particular edge. You can repeat a vertex but not an edge. Okay, so let's see. A, B, C, E. Now, but E only has one to go. So A, B, C, D. Maybe we should start with another node. E would be a good one. I think E is it. We need to find one that has two outgoing edges to start with. C is a good one, right? C has two outgoing edges. So we can now C, E, A, B, C, D is a trail. But it is not a path. Is that okay? Because we have a repeating node here, or repeating vertex. C has repeated. But did we go through the same edge twice? No, we did not go through the same edge twice. The first time, it's going from C to E. The second time it's going from C to D. So we did not revisit the same edge twice. That makes it a trail, but it is still not a path because we are repeating the same vertex inside the walk. Okay, now we have a tour. A tour is a trail, so it has all the qualifications of a trail. But on top of that, we also want the first and the last vertex to be the same. So that means if I back to D, and D can go back to A, right? That makes it a tour. Okay? It kind of makes sense here because when people think about a tour, you're starting from one place, and usually a tour would go back to the same place. So that's so these terms are somewhat relevant to how we use these terms on a daily basis. Are there any questions about these terms? Okay.
How it became a tour when you made it CABCDA? Because the first one and the last one are not the same.
Yeah, that one is a tour already. So we have a tour inside a tour. So this is a tour. It will only cost you $500. This is a longer tour. It will cost you $700.
But it doesn't begin and end with the same vertex.
Yes.
Which one?
CNA.
Second one.
Oh, you're right. Okay, you're right.
Yeah, but
You are correct.
from A to.
Okay, you're right. This is a tour, but the other one is not.
You had 2 tours in there though, technically, because you had an A to an A.
Yeah,
as well.
another tour.
Which one?
You had an A to an A in there as well. Like the C to C was one tour.
Yeah.
And then from A to the last A was another tour.
Right, but the tour has to start and end with the same
So
vertex.
whatever it does.
Right.
You can't have
It's
one
not
time.
just saying that the same vertex can appear twice. It is saying you have to start and end with the same vertex. A planar graph is one that can be drawn in two-dimensional on a plane, basically with no crossing lines. Now, this one is also of particular interest to me because I design circuit boards. Okay, so why do you think designing a circuit board has a particular interest in planar graphs?
It's cross and trace.
Because if you cross the lines, how do you do on the circuit board?
It goes
Layers.
You can do layers, okay, but before we have jumpers, exactly, that's the older technology of using jumpers. So when you have a circuit board, and there's no way you can arrange the circuit board so that you cannot have, so that you won't have crossover lines. So the cheapest solution is to have a single layer board, which means only one side of the copper, has all the routing. And when you need to go from one contact point to another contact point, you just solder a wire from one side and hope solder the other end to the other side. People still make circuit boards like that, but it's getting less and less common because the manufacturing cost of circuit boards, multi-layer circuit boards, has dropped significantly over the past 20-something years. So people have no reasons to go for single-sided board, single-sided PCBs these days anymore. So when you have multi-layers for routing, you have more resources to go over stuff. Can anyone kind of imagine the number of layers of a typical circuit board for a PC motherboard?
9.
Isn't it like 7?
7 is kind of the minimum these days. Okay, so the way it works. Have I explained how multi-layer boards work in this class? No. Okay. So all right. So we start off with the one layer board. Okay. So one layer board is basically what we call a FR4 substrate, which is a fiberglass material. It is non-conductive. So this is the substrate, which is just basically really strong non-conductive material. So what they do is they attach, basically glue on a layer of copper, a really thin layer of copper. You can pay extra money for a thicker layer of copper if you're dealing with a high current situation. And then what they do is they draw a circuit on it, and then they use etching solution to etch away or eat away areas where you do not want to have copper. So in the end, you end up with lines, traces to go from one place to another place. This one goes here, and this one goes all the way around to here, and so on. Okay, and then you solder components on top of that. This is a single layer board. A single layer board has a lot of restrictions. In other words, it is very often that you cannot find a graph to be planar. And as a result, you will have to solder something over the other connections. So so if I have, I'm trying to make this a non-planar graph. So far, it is planar, right, by definition. So I have to be able to draw something that will have to cross over another wire to get to the other side. And at this point, there's no way, the next connection, it doesn't matter where it is, it will still be non-planar. Because if you look at this graph here, or if you look at this picture, there's a way to go from any point to any other point without crossing over another wire. Okay. But there are situations where it is not the case. For instance, if I close this as a loop, okay, let's say that, and you have to connect from here to here, then there's no easy way to do it. So what you do is you have to solder a wire from here to here. It's called a jumper wire. Okay? But you can solve that problem by having another layer of copper. So we call this a bottom layer of a circuit board. So if you add just one more layer, then these two can now be connected through the bottom layer, and you do not have to use a jumper wire anymore. So having two layers for routing your circuits give you a lot more resources. But a lot of times you can run out also pretty quickly. Think about a circuit board for your motherboard, okay? Your motherboard on the regular PC. What is the width of your memory bus? In other words, how many bits of data are we transmitting between the processor and the memory modules for each clock cycle? Well, let's look it up, right? Okay.
Depends. The graphics card's easier because the memory bus is pretty well known.
Well, that's, yeah. So when you go to Newegg, which is a good website to go and check out stuff. So if you go to computer hardware, you go to memory, and we just have to pick the most popular ones. So pick desktop memory, and they usually pick out the first few ones. Those are the most popular ones. So the first one is a 8 gigabyte, separated in two modules, 240-pin DDR3 SDRAM, and if you click on it, it should tell you the width of the memory bus. It doesn't tell you the width of the bus though. It only tells you that it has 240 pins. 240 pins is a lot of pins, okay? Now some of these pins are shared with many other components like power and ground, but a lot of these are data lines and address lines, okay? You need the address line to specify which location on the chip the processor wants to access, and then you need data bus lines in order to transmit the actual content of that location in the memory chip, okay? That's a lot of lines. And then on top of this, you also have a PCI bus. Okay, now I know PCI Express, which is a serial nature, is going to minimize or to reduce the number of wires or traces you need on the circuit board, but it's still a lot. So, and then you look at the size of the processor. How many pins are there with an i7, processor? Well, let's look it up.
Well, hold on. The memory bus width, it's just going to be, it's dual channel width, so it's 64 plus 64 is 128.
Well, dual channel means you need two banks of memory in order to fully utilize it.
Well, yeah, that's two memory modules, so you can.
But each module has 240 pins already.
Right. Well, most modern motherboards use two 64-bit channels, like for 64-bit. Yeah, so they use two 64.
It's only 64.
Yeah. So you give you effective memory bus width of 128.
Okay.
And you got 2011 motherboards use quad channel memory, so that's 4 64-bit memory channel controllers. So there's that. But dual channel is the most common.
Okay, so when we look at processors, this part of the processor specification tells you the number of pins on the processor. This particular processor has 1,150 pins. Now, the concept of having a pin means that electrical contact has to go somewhere else on the motherboard, right? Because otherwise, why would you want to have a pin? Pins are expensive. Okay, so if there's no need for a particular pin, there won't be that pin. So all of these 1,150 connections has to go somewhere on the motherboard. And then each memory module has 240 pins. And all of these things are going, quote unquote, all over the place on the motherboard. So how can you connect all of these things just by routing, the signal from here to here, and then route the other one, to kind of do it in a smart way? How can you do it?
Very carefully?
Very carefully, but also use up a lot of layers, okay? A single layer board is definitely out of the question. 2-layer board, definitely out of the question. 3-layer board, out of the question. a lot of motherboards have at least 7 layers. So when we call a 7-layer board, what it is it has a copper on the top, FR4, as a second layer, another copper here, another FR4, another copper, and so on. So a 7-layer board means there are 7 layers of copper, including the top and the bottom. Okay. Now, how is this going to improve routing? Well, the way they do routing between the layers is to go through what we call vias, VIA vias. And a via can go through from any layer to any other layer. So you can go from this particular layer, have a via, which is basically a drilled hole, and then they put a metallic insert into that hole, and then they soldered that insert so that electrically it is connecting from here down to here. And you can put a via between any 2 layers on a multi-layer board. So you can go from the top layer to the second last layer on the board, and so on. Even with this type of convoluted way of connecting electrical signals, it still takes 7 or more layers in order to route a motherboard.
So it's a graph.
Sorry?
It's a graph this way in, or there's a graph this way?
Yep. And do you think people do this by hand?
No.
Who wants to route 1,000 and something pins on the board?
Insane.
And that's not even counting the other components, right?
Insane people do that.
Insane people would do it, but it would take years to do it too. Okay, so most of the motherboards are what we call auto-routed. In other words, a particular engine is going to figure out how to do it in the best way. And that also relates to graph theory. It also relates to what we talk about in this class, because they are trying to figure out the best way to make use of routing resources. And that's an optimization problem, because there are different ways of doing things. And then on top of all of these things, sometimes auto-routing will give you a design that will minimize the number of layers, but it doesn't work. Why do you think auto-routing sometimes does not work? Even though it successfully electrically connecting all the points, if the length is varying by too much, between 2 data lines or address lines from the processor to the memory, it's going to have a problem. Why do you think that would be a problem?
Degradation.
It's not degradation. It has to do with the time differential between the different signals. Okay, what is the speed of electrons, or what is the speed that you can transmit something over a conductor using electrical signal? I think it's close to the speed of light, right? So it should not be a big deal whether a trace is 7 inches long or 9 inches long. That is not the problem. Okay, it's not the actual length of the trace or the actual time to travel that is the problem. What about the other properties of a wire? Okay, so let's just say that you have a wire, like literally a wire. Okay, you go from here to here, and from A to B, you're sending a pulse, okay, to B. The original pulse looks like a real square wave. What do you think this wave would look like at point B?
There could be a lot of noise in it.
If you ask any software person, that person is going to say, it's going to be a square wave, right? Because it is a perfect conductor. It does not have any of the other weird stuff called capacitance and inductance. But then if you ask a physicist or electrical engineer, they would disagree and say, oh, it's not going to look like this. It's going to look rounded, right? It's going to look like this. Okay? Actually, I drew the opposite way. The shark fin does not belong to that side. It's more like that. Okay? That's because, with any type of conductor, it has, an inherent capacitance and inductance. Those are the things that can degrade or change the shape of the signal. Now, if you think about, having 2 different lines that are related, like 2 lines of the address line or 2 lines of the data lines, one is a lot longer, like this one, and the other one is much shorter, like that one. They all start off as a square wave, but the way they're degraded is different. So by the time it gets here, this one is degraded even more than the other one because it is going through a longer wire. In a computer, how does it know whether something is a 1 or a 0? It has to do with the voltage that it's sensing, right? But how does it work exactly? Well, when you look at something like this, when do you think it will start to recognize this is a 1? Yep.
Surpasses the threshold.
It has a threshold, exactly. Now, the way a threshold works in electronics is kind of interesting. So if you look at the voltage range, okay, so this is 0 volts, and we'll just call it VCC. You know, it doesn't really matter what it is, but there's a particular voltage where everything stabilizes. So when you look at a graph like this, you know, it goes like here, like this one, and it stabilizes. When it needs to turn back to 0, it would drop, and it would dip below, 0 for a very short amount of time, and then go flat, as a 0. The question now is, in terms of time, this axis, the x-axis is time. The question is, at which time this particular device will recognize the incoming signal as a 1 instead of a 0? Okay, sorry?
As soon as you touch VCC.
Nope, it doesn't get to here. There's a certain threshold which is usually around there, and when the electrical signal is more than this, then it will be recognized as a 1. When it drops below a certain point, it will be recognized as a 0. What about in between? If you have a line that is quote-unquote floating, and it's just floating around here all the time, how do you think the component will treat or interpret that particular voltage?
Under voltage.
Who knows? The answer is we don't know. Sometimes it will interpret as a 1, other times it will interpret as a 0.
Other times
So,
it'll just die.
well, that's the problem. So you don't want the signal to be in between for too long. But the other thing that has to do with this graph is, if you look at this graph here, this is the time when the receiving component is going to interpret this particular signal as a 1. So if this is degraded even more, okay, it will change the time. And the timing is everything when you're talking about high-speed memory bus. Okay? Especially when you're talking about DDR type of technology. What is DDR? What does it stand for?
Double data rate.
Double data rate. But how does it work?
It sends and receives. It sends like 2 bits at the same time.
Okay, so normally the way, okay, I know this, I'm digressing a little bit from 440, and this is actually 310 material, but it's okay because it is still computer science, right? So the way it works is, without DDR, every time I want to access memory, I have to do a lot of work. In other words, I have to say, okay, all of you turn to page 20. That is, the information on the address bus. And then I will pick a particular memory chip and say, okay, you are the one that I'm accessing. Tell me what is the content on your page 20. So the rest of the class will just kind of ignore me and go like, okay, it wasn't, you're not telling me to do anything. So you're going to tell me what is the content of page 20, and then guess what I will have to do when I want page 21 on your notebook? I have to go through the whole cycle again. In other words, I have to spend the time again to specify, okay, you all turn to page 21. Wait a little bit because I know it takes time for you guys to turn to page 21. And then I will have to designate you again and say, okay, I just want you to tell me what is on your page 21. Okay? And if I want to access like 4 kilobytes or 512 bytes sequentially like that, I'm going to have to repeat the same process 512 times. Okay, assuming each access is only 1 byte. That's a lot of overhead. So what DDR does is to say, let's make an agreement. Okay, so when the memory bus, I know this screensaver is distracting, so I'm gonna move the mouse here. Not that the Intel processor is not, because I know at least 4 or 5 people in this class are thinking about, I'm gonna put my own computer together, and I'll do it right after class. Yep. Okay, so how do we speed up memory access? Well, we make an agreement, okay? We say that memory bus has a special mode where I don't tell you the address bus anymore because it is quote-unquote implied. So I would just say, okay, I'm turning this into a special mode now. It is called burst mode data transfer. And the agreement is, until I say it is the end of the burst mode, this is the way we do things. I specify the address, I specify who is responsible to give me the answer, and I would just say, I want you to give me the content of page 20 all the way up to page 40, 20 pages, okay? And then what we'll do is we'll agree on the timing of everything. So for every single clock, okay, this is the original DDR. For every single clock, rising clock edge, okay, you are going to read out the next page, and then the next page, and then the next page. But it requires really good time synchronization, because me, as the listening side of this, I also have to keep track of the time in order to understand that, oh, that's the content of page 24, that's the content of page 25, and so on. But the good thing is we're still running on the same clock, which is good because we're still listening to the same tick-tock or the same metronome, so that everything is still synchronized. What about DDR2, DDR3, and so on? Well, they start to use the rising edge and then the falling edge, both. Okay, but that's still good because there are two distinct transitions. And then they start to use the timing between the edges of the clock. So halfway between the rising clock and the falling edge, the rising edge and the falling edge of the clock, it is implied that you will have to give me another page in between. So now I'm starting, so the metronome is going to like tick, 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 tick. But the timing that I have to keep, the timing that you have to keep is now tick-tock, 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 tick-tock. Okay? And in piano lessons, I learned this. And then when you have 4 beats in between, so you have to kind of keep that internal clock going. And when this kind of stuff is happening, what do you think may happen?
Can't keep track of
You
the
might
clock.
lose a beat, right? And if I lose a beat, I might misinterpret the data line and say, oh, this is time for you to transmit the content of page 36. But you are actually on the wrong clock, or the transmission line is the problem. It is delaying or degrading the signal. So when I sample the data line, it might have been in between 2 data items. And that's the problem. And that's why you do not want to have 2 traces of the same bus that have a length difference of more than a certain amount. And that throws a big, huge branch into auto routing, because now not only do we have to connect a point to another point, you also want a particular set of traces to have a tolerance of the distance between a certain length of the trace has to be ensured. Yep.
And then once you add in heat, like doesn't it also like change like the timing too? Like isn't that why like a lot of overclocking you have to be very careful about like cooling?
The heat will also change the resistance of a line, but I'm not sure whether that really plays into copper all that much. Because copper does temperature affects the resistance of most conductors, including copper. But I'm not sure whether it really makes that much of a difference on copper. It might make more of a difference in the semiconductor devices themselves, more than the copper trace that we're dealing with here.
Yeah, when you overclock and stuff like that, it just affects the processor itself. If it's affecting the motherboard, you'll know because
It's unstable.
It won't be working anymore.
Well, the worst thing is it's unstable. It works most of the time and not when you need it to work.
Right.
Yep.
But that's usually not a motherboard thing. If it's a motherboard thing, you've probably fried it.
You can end up with a bus fight. Multiple devices can say, oh, it's time for me to talk on the same wire. Then you have a bus fight. Yep. All right, so are there any questions about all of these terms? Okay, I just kind of went on a tangent on just planar, all by itself. But I think all of these things are related. I mean, everything that I just talked about are definitely still related to graph theory. Any questions up to this point? Questions? So if there are no questions about this, we have already talked about most, if not all, of the topics in graphs. So I'm hoping that we can move on to something else. We talked about Mastermind the other class on Tuesday.
Did you want to play?
I think we finished this one already. So in this case, because we do not have a heuristic, so that means Dijkstra's algorithm is probably a good one to use. A depth first search would also work because the number of vertices is really limited. So even if we go through a depth first search to exhaustively go through every single state or every single vertex, it will still be okay. And it's not a real-time application. It's not like you have to respond within milliseconds. Okay, so it's going to be okay. So that's the end of the discussion of graphs. And then we move on to, oh, some of you have already read it. It's trees. Yay. So the basic concept that we have to talk about would be trees, spanning trees, forests, and traversal strategies. Okay. So I cover all of those topics in this little thing here, which has a lot of links to Wikipedia. But I will at least go through the connections between the concepts. Okay. Be an arborist. Let's start up with a definition of a tree. A tree is a graph, which means every single tree has two components, the set of all the vertices as well as the set of all the edges. But it has some special properties. What makes a tree is there exists at least one R in all the vertices. I choose the letter R because it is a root, okay? So there exists at least one vertex in the vertices that you can choose as the root of a tree, such that there is exactly one path from R, which is the root, to each vertex. That's a typo. Vertex. I originally spelled all vertices, and then I changed it to each. Then I forgot to change the vertices to vertex. So that's why we have a mixture of the two. So this statement, which means, which is basically just saying, from the root, there's only one way, there's only one path, without repeating an edge nor a vertex to any other vertices. It doesn't seem to be a big deal. It's like, okay, it's one restriction, right? But this one single restriction has a lot of consequences. For one thing, it means there will be no cycles in the tree, because a cycle already means there are you can not just have a path, but you can also have a trail and stuff like that. And in this case, you can not have cycles at all. In the case of a directed tree, vertices that have no outgoing edges are called leaves, okay, which resembles what we understand leaves in a tree, okay? Because with any type of node in a tree, you can look outside later on after class. With every single node, you can have branches going out of it. But when you look at a leaf, there are no branches going out of a leaf, okay? It is quote unquote a dead end. So any vertex that has no outgoing edges are called leaves, and all the other vertices are basically just called nodes, which basically means the root can be a node or a leaf. It is a very special case when the root is a leaf, because it means the root is the only vertex in a particular tree. Is that making any sense? I suppose you can call it seed, because a seed is both the root and the quote unquote the leaf, because it doesn't have any branches going out just yet. Yeah, nobody is getting that one. No, there's no such term as a seed in computer science. So there's such a concept, but that's not what it means. Yep. Seeding a random number, that's a seed. Yep. So, but the interesting thing is also in a non-directed tree where the edges are not directed, every single vertex can serve as a root. So you can pick anyone and say, I will consider you as a root, and then you can use that definition in order to go to every other vertex with only one single path. Well, let's take a look, okay? Because this one is probably best illustrated with a picture. So we'll just go ahead and draw a simple tree here. That's a tree. Okay, because the qualification of a tree is there can only be one path from any node to any other node, okay, with an undirected tree. So in this case, it's not directed. You don't see any arrows here. So I'm just asking, are there two ways to go from one particular node or one particular vertex to another vertex? Now, that's pretty clear cut, right? So what I can do is now I can say, I will consider this one as my root. If this is a root, this is the next node, this is the next one, and then we have these three as leaves, right? If I consider this one as the root, then we have this one as the second node, or the second layer of the tree. These three will be the third layer of the tree, and this one will be the last one. So you can basically pick up any vertex in a undirected tree and rearrange everything else so that it looks like a tree again. So that's the whole idea of a non-directed tree where every single vertex can serve as a root. Are we doing okay so far with this concept? And here's a second question, since we just talked about planar graphs, okay? The question is, can you create a tree that is not planar? In other words, there's no way to draw that tree using a two-dimensional draw picture without overlapping. It is not possible. All trees are planar to begin with. How do we prove that? It's a very simple proof. You can prove it by contradiction. Okay, so let's exercise something that we have talked about before, which is proof by contradiction. And we just want to do an intuitive one. It's not going to be a formal one. How do we prove that all trees are planar? What is the first step of proof by contradiction?
Assume that no trees are planar.
Assume the opposite, throw it into the system and see if we have a contradiction, right? So we'll just say that, well, assuming the theorem is not true, which means that there exists at least one tree where it is not planar. Okay, that doesn't sound too bad. So what is the qualification of not being planar?
Have at least one. There are two ways to move something.
So there's one edge that has to fly over everything else in order to connect to the other one, right? And in a tree, there's only one way to connect to every single node. So in order to have to fly over other edges to make the connection, doesn't that mean that one node that you're connecting to has at least two edges connected to it?
Which means it's not a tree.
That means it's not a tree. Yep. So that's proof by contradiction. It's not formal. Okay, you can probably use all the there exists for all the terms to make it more formal, but that's the general idea. Is you throw in the opposite or the negative version of the theorem into the system and say, okay, let's see how where they can lead us. If it leads to a contradiction, which is usually a contradiction of the original assumption, then we have the actual proof. All right, so the next question is, why do we want to study trees? Because if it's not interesting, if it's not useful, we're not going to talk about it. Well, what makes trees interesting and special compared to a general graph is trees can be used to represent a variety of constructs in computer science, and these days, it's also in daily life, okay? Every time you use your computer, which is including your cell phone, and you try to navigate to a particular file, okay? What do you think a file system is, or can be represented as?
A tree.
It is a tree, but why is it not a graph?
Because there's only one way to get into a subfolder from its parent folder. There's no way to go into a separate direction.
Okay. In other words, the other way to put this is for every single file in your file system, there's only one path. Is that making any sense? If you look at the absolute path perspective, every single file only has a single path.
Relative fast.
Well, that's symlink mazes.
Well, symlink is not the bad one. Hard link is the one. Okay, so in other words, I just lied, because in extension 2 and also in NTFS, you can establish what we call a hard link, where you can actually go to the same file from multiple positions. But that's usually not used by a regular user. Okay, an end user usually would not do that. So as far as regular users are concerned, it is a tree instead of a graph.
You can hard link in NTFS? I thought that was only extension 2, 3, and 4. I thought it was only
NTFS has hard links as well.
Good to eat.
Yeah, but most people don't use it because Microsoft does not really support it well.
And they would cry a lot.
Well, it's just not supported. Okay, so the first contact, in terms of because cisp440 is the co-requisite of this class. Did you guys talk about BST, binary search tree, in that class? Okay, that's usually the first one. Go ahead, sorry.
Just recently.
Just recently? Okay, but anyways, before today, that's good. So a BST, a binary search tree, is usually the first type of tree that people talk about because it's easy to understand, and the algorithm to construct, maintain, and traverse a binary search tree are pretty simple. So is everybody exposed to the concept of a binary search tree? So I can kind of make that assumption. Is that okay? Okay, all right. The downside of a binary search tree is, depending on how it is constructed, it can be a linked list. Okay, it can degenerate to a single list, and as such, it is not very helpful because the search time is going to be just linear to the number of items in the list. Okay, so that's why it is okay, but the practical value of a binary search tree is limited. The other type of trees that I think eventually, or at least they might have talked about it already. One is called an Avl tree, which is the initial of the 3 people who invented or who came up with the idea. And then the other one is called a red-black tree. In both of these cases, these trees are what we call self-balancing, which is a remedy of one of the most serious problems of a binary search tree. Is you can create a lopsided tree, and then you lose all the benefits of a tree. But the Avl tree and the red-black tree or RB tree, both of those are self-balancing, which means as you add more nodes or add more information to a tree, it will automatically make sure that the deepest part and the shallowest part of the tree would not be off by a certain number. With RB tree, they can be off by a little bit more than an Avl tree, but it's not enough to really cause any performance issue. Did you guys talk about RB tree, red-black tree, or Avl tree in your order class? Avl? Okay. The reason why they don't talk about red-black tree is because it is actually a bit more complicated than compared to Avl tree. There are more special cases. But the nice thing about red-black tree, which is explained in the paragraph here, is it takes fewer numbers of rotations to quote-unquote keep the tree balanced, because it has a higher tolerance of being not balanced. So that's why it does not take as many rotations. Now the number of rotations doesn't seem to be a big deal when you are just creating the tree and have to maintain it. But when you apply a tree structure to store data in the database or to link all the nodes of a particular file, then it becomes a big deal. Okay, so I'm just going to highlight the paragraph where we are at this point. Okay, this part here. So the smaller number of rotations is important when you are dealing with a file system or a database application where rolling back has to be able, you have to be able to roll back. In the case of rolling back in the journal file system, it's not going to be a big deal because the number of operations is usually really limited. And if your computer crashes and it says, I have to spend a few minutes to check the disk and make sure everything is good again, it's not going to be a big deal. Okay, those few minutes is not going to be a big deal. But when you're dealing with a database and you have to roll back a transaction, then it becomes a big deal because the performance of a database when it's rolling back is going to impact the overall performance of the entire database. I can give you a scenario. So let's say you're buying something from Amazon, and it says right there on Amazon and say only one left. Okay, but you're not the only one who's browsing. Okay, so 20 other people are browsing the same item, and they all saw one left, only one left. So you all try to click on the button at the same time. Okay, you all click, put into cart at the same time. That's okay. It will put into the 20 different carts because nobody's paying yet, right? Why would Amazon stop the other 19 people from putting that thing on the shopping cart when you can put it on the shopping cart and not do anything with it within several months, right? So Amazon is not going to say, oh, sorry, tell the other 19 people and say you cannot have this item anymore because somebody put it into the shopping cart, right? So what Amazon would do is to say, that's fine, all 20 people can put it onto the shopping cart. So let's say that all these 20 people, so the database will go through all the motions to keep track of, okay, now we have 20 orders of this one single item and so on and so forth, right? So when you push the key, when you all press the key of purchase, actually finishing the order, what Amazon would do is to figure out only one person can actually get it. So it might have to undo some of the operations from before because it is not available to the other 19 people anymore. That's only one scenario when you might need to do a rollback in database, is to basically undo some of the operations. That's actually one of the major differences between a commercial product like Oracle and MySQL. MySQL, as far as I know, does not have any ability to roll back. It does not understand the concept of a session, but Oracle does. Okay? But to do this rollback means you have to undo what you just did to a red-black tree, which is the underlying data structure to represent the data. The more operations you have to go through to undo, the slower the performance of the database. Red-black tree turns out to require fewer rotation operations as you insert and delete nodes from the tree, and as a result, red-black tree is the one that is chosen to be used by most database engines. Is that okay so far? I mean, in terms of just the general concepts? Okay. And I have all these hyperlinks to the different type of algorithms or data structures. So Avl tree is one, red-black tree is the other one. Avl tree has a somewhat interesting algorithm. This is graphically representing it, but it's not really a whole lot of cases. You have basically 6 cases of balancing it. When you look at red-black tree, it has more cases to consider. So I'm just trying to look for the section that shows you the complexity. So if you just look at the names of the subroutine, that kind of give you an idea of the complexity of the algorithm. Grandparent, uncle, and so on and so forth. So it has to handle more special cases compared to Avl tree. So these are the reasons why Avl tree, even though on paper it is a more optimal design because the tree is quote unquote more balanced, in reality it is used less often because of the cost of rotation. All right, so let's move on and talk about any practical programming language. It doesn't matter which programming language you use, okay, C, C++, Python, Perl, PHP, and so on. Every single program can be represented by a tree based on what we call productions of the programming language. A production is basically a syntactical rule of the programming language. We don't have to go too far to illustrate this one. We can just look at an expression. Okay? We'll just look at a basic expression that you typically would write in the class. So let's say you're trying to express a plus b divided by c, and then the whole thing you want to raise it to the power of b. Okay? So let's say that's the equation or the formula that you want to represent. Does that look like a tree to you? Well, to the compiler, it is going to be a tree. Okay, so if the compiler is going to look at this as a tree, what is it going to do? What is representing? What is each node or each vertex representing?
An operation.
An operation or a value. Okay. So what we do is, what do you think just from this particular equation, from this formula, what do you think are the leaves?
A, B, C, and D.
A, B, C, D, right? Those are the variables. They are representing something that cannot be divided further into other things. But what I would do is to start with the node, the root here. Okay. What is the last operation that I need to do?
Exponent.
Raising to the power of something, right? So I'm just going to use a caret here to mean to the power of. But in order to raise something to the power of something else, I have two things that I need to specify. What is the number that is being raised to the power of something else? Well, that's a whole big chunk of thing, right? That's the fraction here. So now we have a fraction, which I'm going to use a slash to represent. A fraction has two items, or has two sides. One is the numerator, one is the denominator. What is my numerator?
It's going to be
My numerator is a plus b, which is a plus, and an a and a b. What is my denominator?
C.
It is just c over here. And what am I raising the entire fraction to the power of?
D.
D over here. That's a tree.
Start at the bottom.
Hmm?
You go all the way to the bottom first. On
Right.
one side.
Well, there are different ways. Okay, now this is really a good example. I did not even think of this when I wrote the note. Okay, so when you look at this as a tree, it tells you really several things. Okay, because the tree is representing eventually what you need to do, not how you type up the formula. It's just this is the structure of the operation itself. Okay, but how you write it in a linear fashion, there are several ways to do it. This is one way to do it. This is called the infix notation, which is what we are taught since elementary school. We are taught to say if you want to express the sum of A and B, it is A plus B. But there are two other ways to express the formula. The first alternative is called a prefix format. A prefix format means you specify what you're about to do, then you specify what you're doing it to. So that means, if I want to express this in the prefix format, it is a caret first because that's the last operation. What am I going to do it to? Okay, slash plus AB, and then the C over here, and raising everything to this is the prefix format. And I can work this out really fast because I used to program in Lisp. Exactly. So Lisp is everything in Lisp is expressed in a prefix format. Okay, so that's why I can do this pretty quickly. The other way to express this is going to be what we call the postfix format. Okay, which means you specify la 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 la, then you specify what you're going to do to those things, which is a really awkward way of doing things. How many people have a parent, uncle, or grandparent who's an engineer?
You're talking about like the old Casio and HP calculators that did.
The HP calculators, way in the past, they have what we call RPN or reversed Polish notation. So that's what they do. Okay, they specify the things first, and then you say, what are you doing to those things? So in this particular case, there are several ways to express this. One way to express it is to say A, B. Okay, in other words, you are pushing A and B on what we call a stack. Okay, and then you say, oh, what are we going to do with these? Let's add them together. So what that will do is it will pop A, pop B, and then push the sum of A and B on the stack. So instead of having two items on the stack, now you have only one item on the stack. What am I going to do with that? Well, I'll tell you later, right? Then I push C on the stack as well. So now I have the sum of A and B and C on the stack. And what are we doing with those two? We're dividing. Now we have the quotient of this whole operation on the stack. And then what I do is I push D on the stack, and then what I'm going to do with these two items on the stack to take the power up. So this is one way to express exactly the same operations, but in RPN or reversed Polish notation. How many people still use it on your calculator today? I'm the only dinosaur in this class.
I can't find Windows.
Well, I used to have an HP calculator, and that's why I can look at the equation or formula like this, and do it in RPN as well. Okay, so fast forwarding from my time of using calculators to right now today. Does anyone think that there are still languages out there that are still using the postfix notation?
Lisp is still.
Sorry?
Lisp is still a current language.
No, Lisp is prefix. Okay, you specify the operation before you specify what you're doing to, what you're doing it to. What about postfix notation, where you specify the values first, and then you specify what you're doing with the values? Okay, let me just see if you guys know these, kind of rather computerish, geekish terms. PDF. Okay, what is PDF?
Portable document.
Portable document format. What do we use it for?
Adobe.
It's an Adobe standard, but what do we use it for? To send documents, to print stuff and whatnot.
Turn documents into images.
If you open it up, it is actually RPN underneath. In other words, it will specify coordinates, and then it will say, hey, draw a circle. Where's the center? Where's the radius? other two items that I just mentioned. Okay. What about Postscript, which is kind of the older standard? How many people know what is Postscript? Okay. And what do you use it for?
Printing.
For printing, mostly. Okay. Basically, Postscript is the predecessor of PDF. Okay. And it's the same thing. It is also done by Adobe. And when you open up a Postscript file, it is a text file where everything is expressed in RPM. So even though we do not use it on a regular basis as programmers or as end users, it is used a lot in actual documents or document formats. Why do you think that is the case? I know we're
It's efficient.
close. Sorry?
It's more efficient.
It's more efficient. It is easy to parse as well. Okay, the parser of RPN is actually really, really simple. Same thing goes for prefix. We have to pick the most difficult format to use as human beings, which is the infix format. That is actually the most difficult one to parse from the computer perspective. Yep.
You don't have to represent as many symbols as you do in Infix. Like in Infix notation, you have to have parentheses in order,
Right.
in order to use it. And,
Absolutely.
And reverse